All right, good morning, good afternoon, everyone. So today I'll be discussing some of our ongoing work in our paper published at the ACC 21 conference on July 26th to 29th in Las Vegas, Nevada. So I'm the corresponding author and I'll be presenting our work related to with the title Transformers, Malware in Disguise. So as a general presentation overview, I'll go over the problem and what we hope to achieve. Secondly, methodology and sort of the novelty that we add with our work. Thirdly, the results. And fourth, conclusions and future work. So as a general overview of the problem, in the context of cybersecurity and malware detection, malware variants today include many behavior that we can attribute to something being something called anti-emulation or anti-armoring behavior. So what anti-emulation, anti-armoring is as practitioners or researchers, we want to investigate malware to find exactly what's happening and what's going on. But malware has built-in mechanisms that it can either detect if it's in a virtualized environment and therefore fail to execute at all, or make it much more difficult and burdensome for someone to reverse engineer the malware payload. So for all those reasons, it makes it difficult for us to have a good understanding of exactly what's going on. And next we have something called metamorphic behavior. So malware variants having metamorphic behavior has sort of built-in decryption routines or mutation engines that allow it to decrypt its own payload, decrypt its mutation engine and virus body. It can then take that mutation engine, obfuscate its viral body so that it looks differently, and then it packs itself back up with built-in encryption keys that are included in the malicious binary. So that sort of whole step is sort of summarized with the illustration on the right. So because of all this process, the boundary between malware and benign is becoming blurred. So we're not working with some static form of malware that doesn't change year over year. If you have a malware variant and it has metamorphic behavior, it'll actually look differently to different antivirus vendors, and for even virus researchers, it can look different as well. And that's because metamorphic malware, as I said, avoids detection using forms of obfuscation techniques such as garbage code insertion or instruction substitution or other forms. Even some malware has been known to take certain portions of benignware and add that as a certain percentage of its malicious binary, and even that is enough to sometimes fool some signature-based techniques. So as practitioners and researchers, we're tasked with generalizing models to detect such things. So we want to be able to generalize our models to an extent that we can look at and detect any new zero-day threats. And the word generalizable is very important because as machine learning practitioners, for example, we look at past evidence and label training examples in order to have a good idea on what we hope to achieve when we train our models. But we need our models to be able to generalize to these new and unforeseen threats, and that's because every new zero day is a threat. So things like signature-based techniques are focused on structure of malware, and signature-based just looks at the static form that the malware binary takes before it's executed. So you can look at things like opcode instructions, or something simple as how it's packed and the entropy of different sections. So those would all be examples of static or signature-based techniques. So it looks at the static is how you look at the features, and you develop signatures based off of those findings. But nowadays we're focused more on something called dynamic based. And the reason why we are is because regardless of what the malware hopes to look like when it's deployed from host operating system to host operating system, it can't change its underlying behavior because it needs that behavior to carry out its functionality. So on the illustration to the right, we have this is sort of like a pipeline for one of our sister works and sister papers, where we developed a sandbox environment that allows us to collect, process, and develop models for malicious behavior in a sandbox environment. So as a general problem statement, in Windows, it's worth mentioning as a bit of introduction. In Windows, all activity is done through the Windows API, and that's how we as programmers can interact with the hardware of the machine. And how it operates is files are dynamically linked with one another, where if I have an executable and I need to use a certain set of library files, I can actually grab them from a dynamically linked file or DIL file to fetch the necessary imports that I need to carry out the functionality I do. This saves time, and it reduces the size of binaries, because not every single executable needs to have all the necessary functions included. All it needs is the necessary addresses or hints in order to import it from elsewhere. So anything that needs to be done on the host operating system, let's just say for an event, a certain event, like looking at the registry or something at the file system, needs to interact at a very high level with the host operating system. And then we have something called a stack trace, where you communicate at a very high level, but in the end, they function calls call other function calls, which in the end lead back to the kernel level, which as programmers we don't have access to. We only have at the high level, which is necessary, but in the end everything goes down to the kernel, which actually makes use of the resources. So this is just an example on the right of how we can look at a stack trace, so all the functions that are called from Windows level to the kernel level, and we can resolve those stack traces from their dynamically linked library that they're imported from, to get the exact function name. And that function name and that list sort of tells us exactly what's going on. And this is why I mentioned that these API calls represent what I call the true intent of malware, because that is something that cannot be obfuscated. You could look at certain dynamically linked libraries and say, is this anomalous? But even through means like DIL proxy, malware can obfuscate its own payload within DIL files, and that's readily used. So we look at this problem and looking at the true intent of malware, and then what we do is we look at the sequence of these API calls, and we sort of tell ourselves, well, it tells us a story of the intent of malware and exactly what it wants to do. So similar to how the choice and position of words in a sentence is indicative of meaning or intent, we can sort of say that the use of function API calls in certain sequences is evidence of malicious intent as well. And as just a general example, we could look at a common application of, let's just say, determining if an email is spam or not. You can look at the sentence, even as us humans, because we're very familiar with what's spam or not, that certain words that are used in the context next to other words tells us that it's more likely to be spam. So when we see the words like congratulations, one, and next to an item like an Apple iPhone Pro, we sort of know that's spam, as opposed to something where it's like a pre-authorized utility bill, something very boring, and it doesn't require us to, let's just say, pay something. That sort of tells us that that's not spam, right? And we can train classifiers in order to do that. So we sort of take that same sort of thinking and we apply it to determining if a file is benign or malicious. And we can look at the stack traces and the sequences of those APIs, and we can train a model to tell us exactly what's going on and whether or not there's certain semantics to the way that the stack traces are set up. So one of the sort of architectures that we aim to use in this work is something called a transformer. And the transformer, as used in natural language processing applications, changes the way how we learn semantics from words by taking a sentence with a lot of meaning in it, encodes that representation in a dense form, and then once we, let's just say, for example, we're detecting a next word in a sentence, we sort of feed in the words that lead up to that word to be predicted, and then we decode that representation and assigns a certain probability to what that word should be. So that's the transformer architecture. And other things that make the transformer architecture novel, but we don't quite include all these things in our work, but we do test them out and see if they work, is something called mass learning. Mass learning just suggests that if we want to predict, let's just say, a word in a sentence later on, you maybe want to mask the words after the word to be predicted because you don't know them yet. But in our work, we sort of tested the use of mass learning to see if whether or not we actually needed the full stack trace in order to make the predictions. And we found out it didn't help or hinder us too much. And in real applications, you would have the whole stack trace ideally in order to make that prediction. There's other innovations such as attention heads, which just sort of says how much attention should we pay to the words or the sentences nearby. The more incorporation of attention head that you have, the more long-range dependency you get in your learn model. So one of the other things that we added as a novel application of what we're doing is something called sub-tokenization. So it's not one approach would be look at every single unique Windows API call and encode that as an integer and store it as a dictionary, right? So you'd have something like load library exa, load library a as two example function calls. We could take both of those and just map them as unique entries in our corpus. So that corpus is just the full list of potential words and functions, or words or functions that we're considering in our model. So we could do that. We can map those separately. But the thing is, those two functions have similar meaning under the hood. So it's not just enough to separate them. One thing we could do is separate the root word from the suffix. That way they both share the root word load library, and then we can encode both of those Windows APIs functions with the load library root word, so that when the model trains, it knows that there's some similarity to those, and then it would just, those suffixes, the model would just learn those as well as they are next to load library. So that's just something that we wanted to add, and we found out that when we looked at the entirety of function calls, if you just were to develop a regex pattern that's sub-tokenized based on camel case, the thing is you would actually parse the vast majority of words and develop a new set of a new corpus based off of that separation. But there's other, that table on the right just demonstrate that there's certain exceptions where you may not want to just separate based on camel case, because it quite wouldn't make sense. For example, in the class ordinal, you have something called like ordinal 234 versus something like ordinal 64. Now the 64 in the Windows land means something because 64 is attributed to the 64-bit. So it actually makes a difference that that 64 isn't separated because it might get misattributed to the 64 that's added on to ordinal 64 as an example. So in some cases we have certain exceptions, and these classes hope to cover most of those exceptions and cases. So when we sub-tokenize, we noted what was the increase in the size of the corpus. So on the right, we have the number of unique API function calls if we consider just registry, file system, and thread activity all separate. So for example, if we just white space, so that is, we just take the unique API function calls and just leave them as is, we have something like 1379 unique API calls that are called, and in file system we have 1140. So when you sub-tokenize those respectively, you have 1480 and 18 and 1181, and so that's like an increase in about 40 for each one. The reason why there's not a lot is because you sort of want to set a min frequency value, so that if you have some API function calls that we sub-tokenize and they only end up being present only once in all the training and validation examples, or sorry, in the training examples, what you find is that the model cannot learn just one unique instance. So you want to set a min frequency, and we tested values from 3 to 4, so that the model has a chance to learn them in the context of the stack traces that they're in. We also, in our work, executed 9 enterprise malicious threats, and then we looked at the total number of malicious API calls that were responsible for each of those malware threats, and registry, file system, and thread activity that they're involved in. And this is just to demonstrate that certain malware variants actually execute and then do a lot of things on the host operating system. So they they don't fool the virtualized environment, and they execute and they do all the bad things that they're known to do. But other variants sort of do a few things on the operating system just to check if it's in a virtualized environment, or maybe they sort of make changes to the registry and sort of try to remain persistent so that they can lay dormant and then execute at a later time. So when you have a large selection of malware and you execute them in a virtualized environment, you have to understand that you sort of get those that have anti-armoring and anti-emulation systems built in, but regardless, once they execute, we still are able to collect that activity, and even that activity is evidence of malicious behavior that we can classify. So for our results of baseline, so just as a summary, we took our corpus that we developed based on white space and subtokenize by white spacing and subtokenizing. We sort of developed a vector representation of those, and we fed them into the transformer architecture that I explained a few slides ago. And there's a few hyperparameters that we're focused on that all are attributed to, well, these are mostly sort of the structure of the model. One being the word embedding, which is you take the vector representation and then you embed them into a higher order space. You have something called the hidden dimension, which is just that's a learnable hidden dimension parameter. So that's just again encoding into a higher order feature space and learning those. So that's just simply a dense layer. We have attention heads, which is just to say that sort of adds the attention mechanism that allows us to pay attention to words earlier or later on in this, or I should say function calls earlier or later on in the stack trace, and how much attention should be paid to those. And the transformer encoder layers is just the amount of capacity we add to that encoding and decoding architecture, which is the bulk of the model. So at the bottom here, we just have a demonstration of looking at F1 score for registry, file system, and thread. These are all the unique, again, using the unique corpus. What you find is that the registry tends to outperform the other two. Registry and file system we found outperformed mostly because the malicious API calls that were used were unique to them and not unique to benignware. So again, it's all about context, and we found that when the corpus was larger, closer to that 1300 or 1400 mark, the model performed well. So that's a 96 for registry white space, and 94.9 for the file system white space F1 score. So that's pretty good accuracies just out of the box for our baseline. The other interesting to note is that when we look at the subtokenized scheme, where we added the additional corpus, we actually had poor performance as a result. So for all intents and purposes going forward in this presentation, we'll just ignore the subtokenized results, because across the board they outperformed. They did not outperform just the white space tokenizer, and we'll explain later on why that is. So other things that we looked at was we looked at the baseline, which we can just call model A for now. And then what we did was just sort of decrease the capacity by reducing the number of encoding layers, just to see if, okay, we have our corpus of API calls. Maybe we are sort of overfitting our model just because we were too comfortable using some of the default parameters, and maybe with a corpus of 1300, 1400, and we're not working with a natural language processing problem that is as complicated as, say, the English language. Maybe we can play around with those parameters and see how things go. So we did reduce the parameters by approximately 25% when you did reduce the encoding and decoding layers by 1. But it did decrease performance ever so slightly. So, and this is another thing for all intents and purposes for the rest of the presentation, the registry actually outperformed the file system for every model that we tested. So just for the sake of simplicity and for time, we'll just focus on the registry F1 scores, which I'll highlight with these red boxes. So this is the decrease of performance that we show. The other thing interesting to note is that what we find is that there's a much larger hit to performance for the subtokenized scheme. And that sort of tells us that, again, the subtokenized scheme has only another 40 additional words in its corpus. So for those 40 words to actually be learned, you actually need that additional capacity to learn the intricacies of where they are and where they need to be. So we noticed that across the board, that decrease in performance. So next thing we looked at was when we increased the encoding layer to 3, so we increased capacity, we actually increased performance slightly, but not by much. While something like the embedding dimension did not help when we increased that. And that's because the embedding dimension is actually a function of really the corpus that you're using and your problem, right? So natural language processing applications, sometimes you work with corpuses that are as large as 30,000. So you're working with 30,000 English words or subtokenized versions of English words. So what you see is that the embedding dimension is actually really a function of your problem, and it's not just a parameter that you could just leave by default. So it's really something to be played around with. But when we did increase the number of encoding layers and maybe decrease the number of hidden dimensions, we did note slight increases in performance as high as 96.5 to our best model, but that is also at a cost of 3 times additional parameters that were required to be learned. And finally, when we again, this is just bringing back to subtokenized performance. When we did use higher embedding dimensions, this is just a comparison of model A to C, we did see that large decrease in performance just for the subtokenized version. And it also tells us that perhaps the high number of hidden dimensions is maybe not necessary to learn the semantics of the stack traces, given the simplicity of the corpus size and just the intricacies of the context of the API function calls. Maybe does not need as much capacity as shown here. So we can really look at smaller models and have very good results regardless. So one of the things that we did to summarize everything is that we introduced a novel application of the transformer architecture that's typical in NLP applications. And we did this by learning from stack traces, and we substituted our Windows API function calls and used those as our corpus of words. We also subtokenized the Windows API, and we based that largely based on camel case to cover most bases. And we just wanted to see if it would improve performance. Overall, it was mainly the registry and file system stack traces that showed 96% plus F1 score when we detected malicious stack traces from 9 executed malicious binaries. And just as a quick note, I did forget to mention that we actually also did look at the execution not just on the Windows operating system and everything else in there, but we executed some benignware files such as Remote Desktop Protocol or Adobe Acrobat. So those are shown in the paper, just as an example of executing something else that might seemingly maybe look like malicious activity, like Remote Desktop. So we did use that in our benignware, sort of as our benign files. So given the relatively small size of the corpus, about 1,400 or so, a small model is actually preferred as additional capacity does not help performance and potentially could prove worse off if we add too much capacity, because we won't be able to generalize well. And lastly, as I mentioned previously, subtokenized API calls, when we subtokenize them, they're actually not required and actually hurt performance in the model that we tested out. And maybe that's just not because they're just not relevant for such a small corpus, or you need a more representative data sample where these small numbers of subtokenized APIs occur with a much larger frequency, where the model can actually learn what they are and what they're doing. So finally, I thank everybody for watching. If you have any questions, please send an email to me as the corresponding author at my email. And I thank you everybody for watching.